Hello and good morning, and welcome to INE's webinar for configuring and troubleshooting basic MPLS. For some of you who do not know me, my name is Rohit, and I'm a full-time instructor with INE, and I have 5 CCIE and route switch, security, voice, collaboration, and service provider. Without wasting more time, let's quickly start off with MPLS and configuring MPLS. So what we're going to do is, today in this webinar, I have this topology here, which is actually pre-configured. So I have router 1, which is going to be acting as a customer router, and he has just a default route towards the ISP, which is going to be router 2. So router 2 is going to act as a PE, and XR1 is also going to act as a PE, so which is the provider end. Again, XR2 would be the customer, router 1 would be the customer. The infrastructure between router 2 all the way to XR1 is going to be my ISP infrastructure, which is obviously going to be running MPLS. Now, the first question comes to our mind is, why do we need to run MPLS? What's the need for it? Think about it. Let's say if the customer and the service provider were normally running BGP, you would never have like an IGP running between a customer and ISP. It could either be a default route to the ISP, or you would probably be running BGP with the ISP. So if there was BGP between these routers, let's say there was a BGP running between router 1 and router 2, and the customer was sending BGP routes to the ISP, and ISP has an iBGP neighborship with XR1, so he would pass on those routes to XR1, and XR1 would pass on those routes to XR2. So from a control plane perspective, both the customers, they have the routes to each other, but would they be able to ping each other? No, because the routers in the middle, they are not running BGP. So without MPLS, I would actually need to run BGP on all of these routers. That would be one choice, to run BGP on all the routers and do a full mesh neighborship, which is really not scalable and again, not cost effective. So that would be one choice from an ISP perspective. Or the second choice would be maybe the ISP redistributes BGP into an IGP, which again, would not be a feasible solution, because imagine if you're running OSPF internally, and if I redistribute internet routes into IGP, how many routes would I have? Again, the OSPF would basically receive too many LSAs, and maybe the routers crash. That's where MPLS actually comes in. MPLS is like a kind of a VPN, so kind of encapsulates the actual data or the packets with a label, so that the routers in the transport do not see the actual IP source and IP destination IP. They in fact see a label. So instead of traditionally doing a routing lookup based on the IP, where when I receive a packet, I would normally do a routing lookup based on the destination IP address. But this time, when I receive a packet, I don't receive an IP packet, I receive an MPLS label packet. So MPLS is just like an overlay where you have labels assigned to specific networks. Obviously, labels have to be advertised. So what we would be doing in this webinar, again, because of shortage of time, we would look at pretty basic MPLS configuration, where I have at this point of time pre-configured router 1 with a default route towards router 2. I have pre-configured XR2 with a default route towards XR1. Both router 2 and XR1, they are PE routers, and they are running BGP, VPN, v4 neighborship, which basically means that XR1 has this interface inside a VRF. I have configured this as VRF A. And again, router 2 has this interface in a VRF, which is not in the global table. And that's again A. So from a control plane perspective, 1 has a default route towards 2. XR 2 has a default route towards XR 1. And router 2 and XR 1, they are BGP neighborship. They're forming BGP neighborship with each other. VP and V4 BGP neighborship with each other. And MPLS has not been configured at this point of time. Internally, within the ISP infrastructure, I am running, I believe it's OSPF, which is running internally within the ISP infrastructure. Again, from a CCIE service provider perspective, they would definitely test you with intra-AS, inter-AS also. Obviously, in this topology, we would not be doing inter-AS. We would only be doing intra-AS. But this could also be tested for even CCNP. But it's good to know how MPLS actually functions. So let me quickly go on to my router and show you my configuration before we actually start building MPLS and look at why MPLS neighborship would not form, how the labels are advertised, and how can you troubleshoot MPLS issues. So this is my customer, router 1. If I look at my routing table, show IP route, I have one default route towards the ISP. Looking back at XR2, show route, again, he has a default route towards the ISP. If I look at router 2, which is the PE router, show IP OSPF interface brief, I am actually running OSPF only internally on gig 1.24 and the loopback 0, which you can see here. That's the link towards router 4 and his loopback. So OSPF is not running towards the customer. It's only within the ISP infrastructure. And if I look at my routing table, show IP route OSPF, I have all the routes. I have R3's loopback, R4's loopback, 5, 6, and XR1's loopback, which is 19, 19, 19, 19. So I have everyone's loopback, which means I have basic connectivity all the way from router 2's loopback to XR1's loopback. I have basic connectivity between them. But obviously, the customer to customer, the ping would not work. Where would the traffic get dropped? Let's say if I do a ping from router 1 to XR2's loopback, where would that traffic be dropped? The packet actually comes into router 2. Router 2 does a lookup. Because he received the packet on a VRF-enabled interface, he does a routing lookup in the routing table of VRF A. He would not do a lookup in the global table. So does he have routes to this loopback? He should be having the loopback routes because XR1 must have advertised that. I've actually pre-configured that. The only thing which is not pre-configured is MPLS. So looking back here, if I look at show BGP, VPN, V4, unicast, all, I have the loopback of XR2, which XR1 is actually redistributing in BGP. So all that has been pre-configured. So if I do a trace route, let's say from router 1 to 20, 20, 20, 20, sourcing from my loopback, where does the packet get dropped? IP packet comes to router 2. Router 2 does a routing lookup in the VRF-A's routing table, which you can see here. Show IP route VRF-A. He has the routes to 20, where his next hop is 19, 19, 19, 19. To reach 19, he does a recursive lookup in his global routing table that how do I get to this PGP neighbor, which is the remote peer XR1? How do I get there? To get there, he has to use OSPF, that to get to 19, he should use the next hop as 20.2.4.4 out this interface. Do I have MPLS configured at this point of time? No, which means that router 1 sends an IP packet down here. Router 2 would forward an IP packet to router 4, and then router 4 will have to do a routing lookup. So router 4 does a routing lookup, and does he have routes to destination 2020? No, he does not have those routes. So what is he going to do? He's going to drop that packet. So that packet gets dropped. So because right now I don't have MPLS, I don't have BGP on all the routers. I don't have a redistribution from BGP to OSPF. So router 4 again does not really have the routes in his routing table. So obviously he's going to drop the packet. That's where actually MPLS comes in. Now, MPLS, think of it like OSPF or any routing protocol. What happens, let's say in OSPF, what happens, you and me will first establish OSPF adjacency, right? If I have to give you my routes, you and me need to first form adjacency with each other. Once we establish adjacency, only then I would give you my routes. You would run the SPF, build your database, and then build the routing table. And then you can use that routing table to come back to me. So from a control plane perspective, I am giving you the routes. So the direction of the control plane is from me to you, because I am giving you the routes. And the data plane, which is the, let's say if you do a ping, the data plane is from you to me. So same thing happens in MPLS also. The only difference is that in OSPF, you and me form neighbors, and then I give you my specific routes. I advertise those routes to you. The difference here in MPLS is that we don't advertise routes. However, we advertise labels representing those routes. So for me to advertise you a label representing a specific route, you and me need to first form neighborship. And that neighborship is going to be done using a protocol, like how we have OSPF, which is a protocol used to exchange routes. Similarly here in MPLS, we would use a protocol which could be TDP or could be LDP. Most Cisco routers now don't really support TDP, or TDP is, nobody uses TDP anymore, which is Cisco proprietary. It uses port, TCP port 1711, but LDP, which is a standard, Cisco routers supports LDP also. Non-Cisco routers also support LDP because it is a standard. So what's going to happen is that for you and me to exchange labels representing a route, you and me first need to form neighbors. For that, we need to run the same protocol on both sides. You and me need to run the same protocol. It's like you cannot run OSPF and I run EIGRP and we would form neighbors. You and me both need to use the same protocol to establish adjacency first. Once you form the adjacency, you would then move on to exchanging labels representing a route. So LDP, which is Label Distribution Protocol, uses TCP port 646 for the communication. Since it's using TCP, the most important part here is that the communication between the two routers to form adjacency is done using the router ID, which basically means that the router ID must be a reachable address. If your router ID is not reachable, unlike OSPF, in OSPF, I could just use any router ID and it doesn't really have to be reachable. As long as it is unique within the area, OSPF would form neighbors. But in MPLS, if you're using LDP, it uses TCP port 646, and the communication is done using the router ID, and it has to be a reachable address. So the first thing that you would normally want to do on your routers would be obviously use LDP and build the neighborship. I don't really care about what labels are going to be advertised or how they're going to be advertised at this point of time. My first thing should be, do I have MPLS neighborship between the routers? That's the first thing that you should always test or when you're trying to troubleshoot something, that's the first thing you do, that verify your MPLS LDP neighborship. At this point of time, I have no MPLS configured. So if I actually do a show MPLS LDP neighbor, I do not have any MPLS running. And if I do a show MPLS interfaces, I don't have MPLS activated on any interface. Now, there are two ways to actually activate MPLS, or one could be directly on the interface, which is specific to that interface, or I could do it, or I could use an IGP to automatically activate MPLS. So two different ways. I'll show you both of them. OSPF has that feature that you can actually activate MPLS automatically without going to each and every interfaces and activating MPLS. OSPF has that, ISIS also has that. So you can enable MPLS through OSPF. Right now on router 2, let me in fact show you, the only place that I need to activate MPLS is on my transit link, which is the link between 2 and 4. That's the only place I need to activate MPLS, because that's where I would form neighbors. You never activate MPLS towards customer, because customer would not run MPLS. I mean, unless it is, let's say if it was an inter-AS communication, you had multiple service providers, there could be a possibility where you may have MPLS, but most of the time you would not have. So you would probably go to option A, B, or C to have communication transiting multiple service providers. But towards the customer, you never run MPLS. So the only place I need to enable MPLS is on the physical interface, the transport link towards my internal infrastructure within the ISP infrastructure. And that is done by going to the interface gig 1.24, and giving the command MPLS IP. Now, the minute I give MPLS IP, it actually activates LDP. It uses LDP. It's not using TDP. Its default is LDP. But there are a few commands that I highly recommend that you should do before you activate MPLS. There are a few commands that you should do. Let me in fact do that first. The reason I like to do those commands is because it really becomes easy to troubleshoot MPLS issues if you actually do those things, especially in the lab environment. Maybe in production, you don't really need to do it, but lab environment, you should definitely do these things. It just becomes easier to troubleshoot when you look at maybe a debug MPLS packet or do a trace route, and you can identify which label originates from which router. So a few things that I would do always. MPLS requires Ceph to be enabled. Ceph should be enabled, otherwise MPLS would not really work. So again, Ceph is enabled by default, but again, from a lab exam perspective, I don't really trust what's pre-configured. In the lab exam, you should always trust the diagram, trust the question paper, don't trust what's pre-configured, because sometimes they may disable Ceph and you really end up wasting 2 hours or maybe half an hour trying to fix MPLS when your Ceph is disabled because you assumed that Ceph was enabled by default. It is, but I don't really trust what's pre-configured. So always have the habit of starting off with IP Ceph distributed. That's the first thing you should do. Ensure Ceph is enabled. And then give the command MPLS label protocol as LDP. So I am using LDP. MPLS LDP router ID, you should use a unique router ID, and it should be a reachable address because of the TCP connection on 646. I'll show you the problem that you may face if your router ID is not reachable. So MPLS LDP router ID, let's use loopback 0 and force this. So right now, loopback 0, which is, I believe, 2.2.2.2, and that's going to be my router ID, and that is running OSPF, which if you look back up here, I was running OSPF on, I believe it was somewhere here. So to show IP OSPF interface brief, I am running OSPF on my loopback. Okay, so these are the few things that you should do. You should enable Ceph. You should define the MPLS LDP protocol. You should define a reachable router ID as maybe the loopback. Obviously, loopback is preferred if you have redundant paths. And besides this, one extra command that you should do before you activate MPLS label range. I highly recommend you give this command because the way the labels are advertised, the label value or the label range value, it is not unique. It is unique to the router, but not unique between routers. So let's say if router 2 is advertising a label to router 4 representing his loopback 2.2.2.2, and let's say he advertises a label number 16, it starts from 16 by default, and let's say he gives 16, when router 4 advertises that label to his neighbor, he would also give 16. It's not a problem because labels don't have to be unique. It has to be unique on the same router for different prefixes, but it does not need to be unique between routers. So the reason I recommend giving a unique label range is because it just becomes easier to troubleshoot when you look at a debug MPLS packet or even a trace route. It just becomes easier because you know, okay, this label is from router 2. So what I normally do is I always give a unique label range for each of the router. Obviously, this label range should be enough. Don't just give like 2000 to maybe 2001. This would be problematic because I don't have just 2 routes. I have more than 2 routes. So you should probably give enough range, which should be equivalent to the number of routes that you have within your ISP infrastructure and the number of customers that you have. So it should be enough. Now, I know that in the lab exam, you would never have routes more than 1,000. It would probably be around 200 or 300 routes. So I know that in the lab, you would never have more than 1,000. So what I normally do is I give something from 2,000 to 2,999. So this becomes like a 1,000 range of labels for router 2, which is unique to router 2. After this, I would go and activate MPLS, which is done with MPLS IP. So now when MPLS gets activated, he would start sending LDP packets or the connection packets, which is going to be on TCP 646 to whoever his neighbor is. But that neighbor right now is not configured for MPLS. So this is one way of actually activating MPLS. The second way would be that I actually activate using a routing protocol. Now, there are 2 routing protocols that actually support activating MPLS through the protocol, which is OSPF and ISIS. So instead of me giving MPLS IP under each and every interface, maybe I had multiple interfaces to router 4. So instead of doing it on every interface, I could just go to router OSPF 1 and give the command MPLS LDP Autoconfig. What this command does is whichever interface has OSPF running, so show IP OSPF interface brief, whichever interface has OSPF running, those interfaces would have MPLS activated automatically. So if I actually do a show MPLS interfaces now, you would see that my gig 1.24 has LDP enabled automatically through OSPF. It did not activate on the loopback. You cannot activate MPLS on the loopback. However, even if I go and try doing that, let's say if I go to my loopback and manually give the command MPLS IP, it won't accept it. MPLS cannot be enabled on loopback interfaces. However, the loopback would still be a label advertised for this loopback. Why is that? There are two conditions for a label to be advertised for the loopback. Number one, it should be running in IGP. Are we running IGP on loopback? Yes, OSPF. The second condition is it must be a /32 address. If it is a /32 address, then it would have a label assigned to that loopback automatically. But for the physical interfaces, the transport links, for that, you have to activate MPLS because you're actually forming LDP neighborship. So you have to activate MPLS. But on the loopback, you don't need to activate, or you cannot activate. It will still advertise a label for the loopback if it has OSPF or any IGP, and it is a /32. So my loopback is a /32. That's why there would be a label for this loopback also. But you would not see, if you do a show MPLS interface, you would not see MPLS activated on that interface. So if I actually do a show MPLS LDP neighbor, at this point of time, I don't have any neighbor because the remote router is not configured for MPLS LDP, and he does not have MPLS activated. It's the same concept like OSPF, where if I have OSPF running and you don't, we would not form neighbors. Both have to be configured for MPLS or LDP. So I would go to my next neighbor, which is router 4, and I would activate MPLS on both my interfaces. One is towards router 2, and one is towards router 3. I don't have to activate on the loopback. Let's go to 4, and again, give the command ipsef distributed MPLS label protocol, LDP, MPLS LDP router ID loopback 0, FOS, and MPLS label range. I'll give a unique label range, 4000 to 4999. And lastly, go to my interface, gig 1.24. Again, I could go to my interface and give MPLS IP, and then 34 MPLS IP. I could do it like this, or I could do it under the OSPF process. Obviously, the OSPF process, it saves time because imagine if you have like hundreds of routers and you have to go to like 20 interfaces, it kind of becomes difficult to, or maybe it's not scalable to actually go to every interface. All right, so now I have MPLS running between 2 and 4. Let's go now and do a show MPLS interface, or show MPLS LDP neighbor. So show MPLS LDP neighbor, you would now see that I have an MPLS LDP neighborship between 2 and 4. The first line is the one which is important. That's the line that shows you that my connection or my router ID of my device. So my router ID is 2.2.2.2 because I use the loopback force command. And the remote device's router ID is 4.4.4.4. The second line is even more important. That's where your TCP connection is. So look at the connection. The connection was between the loopback of router 4, whose source port is this one. Destination was the router ID of loopback 2. Destination port was 646. So what's actually happening here is that they both are sending neighborship requests to each other. Destination port is 646, but the connection is made on the router ID. That's why the router ID has to be a reachable address. All right, so now I have my MPLS enabled between 2 and 4. Let's try and enable MPLS between now 4 and 3, 3 and 6, 6 and 5, and 5 and XR1. Let's go to 3. Now on R3, I'll just use the OSPF command. You don't really have to do MPLS IP. So it's like I could do MPLS IP and you could use the OSPF command. It doesn't have to be the same. As long as we have MPLS enabled and the same protocol, we would establish adjacency. So let's do a router OSPF1 MPLS LDP Autoconfig. You would see that it forms neighbors with router 4 automatically. And again, show MPLS LDP neighbor. I have my neighborship with router 4 and the connection is on the loopback. Or in fact, you shouldn't say the loopback, you should say the router ID, because your loopback may be different from your TCP connection. Okay, so I have 3 configured. Let's go to 6, which is the next router. Router OSPF1, MPLS LDP Autoconfig. And then router 5, MPLS LDP Autoconfig. And lastly, we have XR1. Obviously, we should still give other commands like ceph, label protocol, and label range, and the router ID. We should define that. If you don't define that, he would still use the loopback as the router ID if it has OSPF running and if it's a /32. So the last router is XR1. So XR1 is kind of a bit different. I mean, the concept is still the same, but the command is different. So if you look at show run router OSPF, this is how I configure my OSPF on iOS XR. So I could go and enable autoconfig under the OSPF the same way, but the command would be router OSPF1, and here I would go to my interface and say autoconfig, or I could do it under the area as MPLS LDP autoconfig. But if you want to do it specifically for an interface, the command would be MPLS label. First, you should define the label range. Let's say 19,000 to 19,999. And then say MPLS LDP. Define the router ID, which would be 19.19.19.19. And then enable MPLS for the interface towards router 5. Once I have MPLS enabled, all I need is to commit for the changes to apply, and I should form LDP adjacency with XR1, which you can see here. I have established adjacency. So now I have MPLS running on all my interfaces within the ISP infrastructure, end to end. I have MPLS running all the way from here. Everywhere I'm running MPLS between the 2 PEs. Now, since I'm running MPLS, would my ping work between customer to customer? Yes, it would work. So what we have to actually understand is how the labels are advertised. So we would look at that. But before I show you that, I just want to quickly touch base on troubleshooting neighborship issues, or why your MPLS LDP neighborship would not form. There are many reasons why your LDP neighborship would not form. The first would be that maybe you don't have MPLS enabled. So always do maybe a show MPLS LDP neighborship. You can use this command to identify your neighbors. Are you establishing neighbors? Or you could do a show MPLS interface to identify that if MPLS is running. There's another way to actually quickly identify where is your MPLS broken. There's a quick way to identify that. So let me in fact show you that. I will first do a trace route from router 1 to XR2, which is customer to customer. My trace route works. And look at the label stacks. I have this is my transport label, and this is my VPN label. VPN label was advertised between the PEs, which is router 2 and XR1. I'll actually show you how it does that in a bit. But this is your transport label, your MPLS label, and this is your VPN label. Because my customers are in a VRF, they're not in the global table, so router 2 and XR1 would exchange VPN labels with each other through BGP and not through LDP. They are exchanged. This label was exchanged through BGP, and this label was exchanged through LDP, which is MPLS. So what I see here is that router 1, when he does a ping or a trace route, he sends an IP packet to ISP. I don't see MPLS there. Why is he sending an IP packet? Because I don't have MPLS running between the two routers. So he's sending an IP packet. When the ISP receives the packet, he sees that, okay, this packet is destined for my remote PE customer, and that PE has told me that I should encapsulate the packet with a VPN label 19,014, and on top of that, I should put an MPLS label 4004, which actually came from router 4. So he puts an MPLS label and forwards an MPLS label packet to router 4. Router 4 does a swap and forwards that to router 6. Router 6 does a swap, forwards that to router 5, and router 5 removes the transport label and forwards a VPN label packet to the ISP, which is XR1. Excuse me. So I'll actually explain this field in a bit. This is just a quick overview of what's happening behind the scenes, but we'll actually draw a table and see how these labels are advertised. So right now I can ping between the customers. You see, I don't have BGP running within the ISP infrastructure. I don't have BGP on the PE routers. I only have BGP between the PEs, which is router 2 and XR1. But because of MPLS, I have my ping between customers work because the packet gets encapsulated with the VPN label, and on top of that, a transport label. So let me show you a quick way to identify first the LDP neighborship issues. Like I said, one way would be verify, do you have LDP neighborship? Verify if you have MPLS enabled on the interface. But there's one quick way. Let's say I'm going to break the LDP neighborship between maybe 3 and 6. I'll break the LDP neighborship here. So here I have MPLS LDP neighborship broken. My link is still up. My OSPF is still working, but my LDP has gone down. And if you remember, I told you that LDP uses the router ID for the TCP connection. Let's say I go to router 3 and I give the command, I make a new loopback, let's say loopback 1, IP address 33, 33, 33, 33, 255, 255, 255, 255. And we should not have OSPF on this interface. Maybe that interface is not running OSPF, so I will just modify this to not do a network 0000. And instead, I would just do network 20.0.0.0, 0.255.255.255, area 0. And network 3333, area 0. So what I've actually done is I have activated OSPF on only my loopback 0 and my transit links. I have not activated OSPF on my new loopback, which is loopback 1. Loopback 1 has an IP address of 33, 33, 33, 33, which is not running OSPF, which is not being advertised in OSPF. And let's say now I go and say MPLS LDP router ID loopback 1 force. What's going to happen? Will I establish LDP neighborship with the remote person? No. If I check my show MPLS LDP neighbor, I do not have the MPLS LDP neighborship between router 3 and 6 and maybe 3 and 4. I don't have LDP, so my LDP is broken here. It is broken between 3 and 6. It is broken between 3 and 4 because router 3's loopback 1 is the router ID, and that loopback 1 is not reachable. So you would not form LDP neighborship. So how can I identify? Because imagine if you were maybe in production or even in the lab exam, you have like 30, 40 routers. Do you really think that you should go to every router and do a show MPLS LDP neighbor, show MPLS interface? It just takes too much time. So there has to be a better and a faster way of identifying where is LDP broken. What you could do is go to any of the PEs, so R2 or XR1, and do a ping MPLS. So instead of doing a normal ping, do a ping MPLS, and do a ping to the remote PE's loopback, which is IPv4, which is 19, 19, 19, 19, which is the remote PE, XR1's loopback. And the mask would be 255, 255, 255, 255. Source would be your loopback, 2.2.2.2, and Warbros. When you give this command, it actually tells you where the problem is. What do I get? I see B. What does B say? Unlabeled output interface. So the packet was okay all the way till 20.2.4.4. So till 22.4.4, it was okay. I got a reply. But which basically means that MPLS is okay from here to here because I got a reply from this interface. But the outbound interface on R4, that's the link that has a problem. Output interface, which you can see in here, B indicates unlabeled output interface. So my outbound on R4 towards R3, that's the link that has a problem. So I could quickly go and maybe identify the problem on that link. So maybe I go to router 4 and do a show MPLS interface. Do I have MPLS on 34? Yes. Maybe on 3. Show MPLS interface. Do I have MPLS enabled on 34 and 36? Yes. So I see MPLS is enabled, but my neighborship is not forming. Right? Because if I do a show MPLS LDP neighbor, I do not have my neighborship because my TCP connection is failing. So how do I fix this? One way would be, okay, I change my router ID to be loopback 0. In that case, yes, your neighborship would form. The second way of fixing it would be maybe I advertise loopback 1 in OSPF. In that case, my neighborship would come up, no problem. But what if you had some kind of restriction which said, do not advertise this loopback 1 in OSPF and ensure that your router ID is loopback 1. So I cannot change my router ID and I cannot advertise in OSPF. What do I do in that case? In that case, what I could do is change my TCP connection to use not the router ID, but maybe the physical interface. So what I could do is go back to my interface 34 and give the command MPLS LDP discovery transport address would be the interface. Same thing on 36. My transport address would be 36. And now you would see that your MPLS LDP neighborship comes up between 3 and 4 and 3 and 6. It should come up now. It came up with 4, it came up with 6. If I do a show MPLS LDP neighbor now, you would see in the first line, my router ID is still loopback 1, but my TCP connection is on the physical interface, which you can see here. So my TCP is not using the router ID now, but my router ID is still loopback 1. So these are the kind of things that you normally would face in lab exam. I mean, I don't really see this as an issue or as a restriction in production, but there could be a problem like this in production also, where you probably use one of the interfaces that is not running IGP, and that's causing your LDP neighborship to fail. Okay, so now I have my MPLS up and running. Again, if I go back and now and do the ping MPLS, I should see it like this. So I should see it like this, which basically means that it was a success all the way to XR1. So this is a quick way to identify LDP neighborship issues. That's a really quick way. I don't recommend you going to every router and doing a show MPLS LDP neighbor. That just takes too long and too much time, and you're really fighting against time in the lab exam. So you really have to know quick ways of identifying issues. So now that I have my MPLS up and running, I have the ping between the customers. Let's look at now the MPLS routing table or the forwarding table and how these labels are actually advertised. So you remember when I did a trace route, I was seeing a transport label and I was seeing a VPN label. So there are 2 label stacks on top of my IP packet. One was a VPN label. So on top of my IP packet, there was a VPN label. And on top of that was a transport label. So let's see how that gets built. So what I'm going to show you right now is something like OSPF. Like you and me establish OSPF adjacency, and then I give you my route. You build your database, and then your routing table. The same thing happens here. You and me establish LDP neighborship. I give you a label representing that route, and then you build your database, which is like your MPLS forwarding table, and your data plane uses that forwarding table. So let's see how we can try and draw this diagram. So we have, I believe, customer here. We have router 2, which is the PE. I have 4. I have 3, 6, 5, XR1, and XR2. So I believe we are running internally, we are running OSPF. So we have OSPF and we have MPLS. Between my 2 and XR1, I have BGP, VPN, V4 neighborship. Okay, this is what is configured right now. And so right now, I'll actually explain this without my customer being in a VRF. Let's say if the customer was in the global table, would there be a VPN label? No, there would only be one label, which is the transport label. So let's say the customers were in the global table. Okay, let's see how the labels are going to be advertised. I'm going to draw the MPLS forwarding table here, and we will see how this works. Let's call these routers here. Let's say routers. I have R4, 3, 6, 5, and XR1. So here I have my local label. I have my out label. And then we have the prefix. I have the interface. And then I have, I believe I have the next hop. Now, what I'm showing you right now is only from perspective of R2's loopback label advertise towards R4. So I'm not talking about data plane at this point of time. What I'm talking about, okay, 2 and 4 have established LDP neighborship, and now R2 advertises a label for his loopback. The same process happens for every interface within the IGP infrastructure, which wherever we have MPLS. But I'm just showing you from one loopback's perspective. So from this loopback, which is 150.1, or in fact, it is not 150, it is 2.2.2.2. So 2.2.2.2, again 2.2.2.2. Two dot two dot two dot two and 2.2.2.2. Okay, so what's going to happen right now is R2, when he advertises a label representing his loopback to his neighbor, which is R4, because this loopback is directly connected to router 2, he advertises a special label. And that label is label number 3, which is called as implicit null. If you look at the label range actually starts from 16 onwards. If you do a MPLS label range question mark, you would see that it actually starts from 16 onwards. 1 to 15 was reserved because for special use case. So for R2, his own loopback is directly connected to himself. So he advertises a special label called label number 3, which is implicit null. So label number 3 or implicit null is, you would not see it locally here. You would not see in the MPLS forwarding table, but you would see it on R4. So when R4 gets an implicit null, so I'm just going to write it here, implicit null. Okay, so when R4 gets an advertisement of a label, he gets, okay, R2 has advertised implicit null for the loopback 2.2.2.2. So he puts a special message here in the out column called pop label. Now, the meaning of pop label is that remove the topmost layer only. Remove the topmost layer only. Okay? And now R4 has to advertise that to his neighbor. See, think of it like OSPF. I give you the route and you have to give my route to your neighbor, right? Same thing happens here. R2 is advertising a label for his loopback to R4. R4 has to advertise a label for R2's loopback to R3. But is that loopback of R2, is that directly connected to R4? Is it? No. So he cannot send implicit null. You can only send implicit null if you are advertising a label for your directly connected interface. For R4, 2.2 is not directly connected. So he has to advertise a label from this range. So we had given a unique range, I believe, 4,000 to 4,999 on R4. So let's say he advertises a label 4000 representing 2.2.2.2. So whatever he advertises to his downstream neighbor, R3, he puts that in the local column here. And R4 had received the update of the label from who? From R2, right? On which interface? On gig 1.24, he puts that here. Next hop was 20.2.4.2. And now he generates a label 4000 and advertises to R3. So R3 receives a label 4000 representing 2.2.2.2. On which interface did he receive it? On this one, which is gig 1.34 from the neighbor 20.3.4.4. Now for R3, that loopback is not directly connected. So again, he advertises a label to his neighbor. Let's say 3000. And he gives it to R6. So R6 gets 3000 from gig 1.36 on 20.3.6.3. 6 advertises to R5 a label range 6000. He puts that here. And this is gig 1.56, which is 20.5.6.6. 5 gives it to XR1, let's say 5000, which will come here. And this would be gig 0 by 0 by 0 by 0.519. And on 20.5.19.5. And this would be, now, in fact, XR1 will also generate a label for 2.2.2.2, maybe let's say 19,000. And but this label is irrelevant because there's no neighbor behind XR1. There's no neighbor behind XR1. So this local label is irrelevant, but he still generates that because in the future, if a new neighbor gets added to XR1, he would give him 19,000 representing this loopback. So this is how it actually builds the MPLS forwarding table. So whatever I advertise to my neighbor, I would put that in the local column. Whatever I receive from my neighbor, I put that in the out label column. And this whole process happens for every interface within the ISP infrastructure. Now coming to how my data packets, if you, like I told you earlier, that OSPF first receives the route, builds his database, builds the routing table, and then when you do a ping, the ping uses the routing table. Similarly here, we have LDP neighborship, we exchange labels, and we build the MPLS forwarding table. And then if I do a ping from customer to customer, the ISP would use the MPLS forwarding table. So let's see how it actually uses that. So let's assume that we do a ping from XR2 to router 1. Let me in fact first copy this. I'm just going to copy this this screen so we can write on that. And let's go to my Dropbox screenshots. All right, so okay, so let's write on this. Let's use green. So let's say XR2 does a ping to router 1. Does he have routes to router 1? Yes, he has a default route to ISP. Am I running MPLS here? No. So what does he send? He sends an IP packet. IP packet to XR1. On which interface did XR1 receive the IP packet? XR1 receives it on this interface. Is this interface in the global table or in a VRF? It is in the global table, assumingly. It is in the global table. So XR1 does a routing lookup in the global table. Do I have routes to 1111, which is router 1's routes? Yes, through BGP. Obviously, if this was the global table neighborship, then this would be IPv4 neighborship. This would not be a VPN-v4, it would be an IPv4. So because XR1 received it on an interface which is in the global table, he does a routing lookup in the global table. Do I have routes to 1111? Yes. Learn through BGP IPv4 R2. Is R2, the next hop is 2.2.2.2, correct? Through BGP. But is 2.2 directly connected? No. How do I get to 2.2.2.2? To get there, I have to use OSPF and forward it out to the next hop, R5. Once the packet reaches here, to go out that interface, it finds that MPLS is enabled on that interface, which means I cannot send an IP packet to R5 because MPLS is enabled here. So now he looks for a label. What's the label for the next hop that BGP provided? See, there are two next hop involved here. The first next hop for XR1 is 2.2. To reach 2.2, the next hop is R5. You always do an MPLS lookup for the next hop for the final destination. So the next hop for 1.1.1.1 was 2.2.2.2. And the next hop to reach 2.2 was R5. You always do an MPLS lookup for the next hop, which is for the final destination. So now, because MPLS is enabled, he cannot send an IP packet. He has to encapsulate. So now he looks at his MPLS forwarding table. What is the label for 2.2.2.2? The label is 5000. So now he encapsulates the IP packet with an MPLS label, and R5 receives IP inside and label 5000. So now what did R5 receive? Did he receive an IP packet? No. He received an MPLS labeled packet, which is a transport label. What does R5 do? He will not do a routing lookup because he received an MPLS labeled packet. So he does an MPLS lookup. If I receive 5000, swap it with 6000 and forward it out to this interface to this neighbor. So now R5 swaps the label and sends to 6, again an MPLS labeled packet, 6000. What does R6 do? Checks his database. If I receive 6000, swap it with 3000 and forward it out to R3. Again, an MPLS labeled packet comes to R3. IP 3000. R3 does the same thing. Swap it with 4000. When R4 gets it, he sees that if I receive 4000, do a pop label, which means remove the topmost layer, and whatever's inside, don't look at it, just forward it out to router 2. So now R2 gets an IP packet. So R2 directly does a routing lookup now. And does he have routes to R1? Yes. So he forwards an IP packet to customer. This is what is happening behind the scenes. But this changes a bit when you have the customer not in the global table, but maybe in a VRF or in a unique routing table. So if you notice, or you may think that why is router 2 sending implicit null? And why is R4 doing a pop label? Like I said earlier, that R2, for him, the loopback is directly connected, so he will advertise implicit null, which is a special meaning. The reason he does that is to offload some of your processing to the next hop router or to your penultimate hop router. This process of popping label is called as PHP, which is penultimate hop popping. The reason it does that, imagine if this process was not there. Let's say if R2, instead of sending implicit null, he advertises 2000. which means here you would see 2000, correct? Which means R4 would send an MPLS labeled packet 2000. What would R2 need to do? He would have to remove MPLS, so remove the encapsulation, do a routing lookup. So first he has to do an MPLS lookup, then remove the MPLS label, then do a routing lookup, and then forward the packet to R1. Now, if you look at your PE routers, there's a lot of load on these routers because we have BGP running, we have VPN v4 running, we have 500,000 BGP routes, we have OSPF running, we have MPLS running. So to offload some of your processing, what R2 does is he sends an implicit null to tell the R4 that when you send me the packet, remove the topmost layer. So one job is less for R2. He does not need to remove the MPLS label now. He directly gets an IP packet. Okay, so this is the process when you have no VPN v4. Let's look at the process when you have VPN v4. So this time I have this interface in VRF A, and this is also in A. What's the difference? Now, this process is the same. This is a transport label process. But R2, because now this customer is inside a VRF, he's not in the global table, R2, through BGP, will advertise, not through MPLS, LDP. LDP is only for transport. Through BGP, he will advertise a VPN label to his XR1 neighbor. So here, he will put, let's say 19,000, in fact, let's put a label, 2099. And here you would see something like V. V indicates this is not a transport label, it is a VPN label. In the out column, you would see the message, no label. For the prefix, one customer's prefix, 1.1.1.1. Interface is gig 1.12. Next hop is 10.1.2.1 customer. And this label would be advertised not to R4, directly through BGP to XR1. So only XR1 will receive 2099, which is a VPN label for the prefix 1.1.1.1. And outbound interface is gig 0x0x0x0.519. Next hop is 2.2.2.2, which is BGP. So, I mean, technically, this is, it's not going to be in your BGP table. It's not going to be in your MPLS forwarding table. So you would not see this. You'd only see this, and the next hop. So this is advertised via BGP, not via MPLS. So now how does the traffic flow? XR2 does a ping to router 1. Is there MPLS running that? No. So IP packet comes to XR1. This is IP packet. XR1 this time has received the packet on a VRF enabled interface. So he does a routing lookup in his VRF A's routing table. Do I have routes to 1111? Yes, through BGP. And next hop is 2.2.2.2. However, the next hop 2.2.2.2 has instructed me, XR1, that if you want to send packets to my customer, you must encapsulate with the VPN label that I have given you. So now XR1 encapsulates IP packet with a VPN label 2099. With a VPN label 2099, which he got from BGP, that I must encapsulate with 2099. To reach 2.2.2.2, he must now encapsulate with an MPLS label, which is 5000. So he puts transport label 5000 here and forwards to 5. What does 5 get? He does not get a VPN label. He gets a MPLS label, transport label. So he does a swap. So this remains the same I have IP, I have 2099, and this would become 6000. 6 does the same thing, swaps the transport label. A VPN label does not change. So when he forwards it here, this remains the same, IP 2099, and this becomes 3000. And then this guy does the same thing, IP 2099, and this would be 4000. What does R4 do? Pop label. So R4 removes the topmost layer. Pop label means what? Remove the topmost layer. And he sends a VPN labeled packet 2099 to R2. R2 does a lookup. 2099 is a VPN label. Out label is no label. The meaning of no label versus pop label. Pop label means remove the topmost layer. No label means remove everything. So now R2 removes everything, strips off the VPN label, and forwards out to this interface towards this customer, and that is an IP packet going to customer. This is the process which is happening behind the scenes. So let's look at our router now and look at the MPLS forwarding table. I'm going to go back and let's shut this. And let's look at our routing table, which you can see here. I did a trace route from router 1 to XR1, or if I do it from here, XR2, trace route to 1111, source 20, 20, 20, 20. Look at what's happening behind the scenes. IP packet from XR2 was received by who? XR1. This is XR1's IP. It's an IP. There's no MPLS label here. It's an IP packet. What does XR1 do? Which you see here, XR1 encapsulates with a VPN label 2001, and on top of that, a transport label given by R5. If you notice, 2XXX or the label range, this belongs to R2. So this came directly from R2, which you can see here. If I do a show MPLS forwarding table, or in fact on XR1, if I do a show MPLS forwarding table, I don't see a label for 2001 because it's not in MPLS. It's learned via BGP. You would see that in show BGP, VPN, V4, unicast, and let's do labels. You'll see that the label to reach this customer 1111, R2 next hop has advertised a label 2001. This has come from BGP. So R2 gave that to XR1, the remote PE, that if you want to send packets to my customer, you will encapsulate with the VPN label 2001, which is what we see here, 2001. Now to reach this next hop 2.2.2.2, it does an MPLS lookup because the interface between XR1 and R5 that has MPLS enabled, so he cannot send a VPN label packet. He has to further encapsulate. So he sees, okay, what's the label for 2002? 5001, which is my out label, which means it must have received from R5. So he puts that label, which you see here, 5001, and now XR1 forwards to R5. What does R5 receive? R5 is not running BGP. He's only running MPLS. He received a labeled 5001, right? If I receive 5001, swap it with 6001 and forward it out to R6. R6, show MPLS forwarding table, receive 6001, swap it with 3005, forward out to R3. R3, if I receive 3001, or in fact it was 3005, change it to 4000 and send it to R4. R4 says, if I receive 4000, do a pop label. Who gave him this pop label message? R2. For what? For his loopback. Because for R2 is directly connected. Do a pop label, which means remove the topmost layer. And what's inside? VPN label packet, which you see here. So I have VPN label, on top of that, transport label. I have VPN label, swap happened. I have VPN label, swap happened. I have VPN label, swap happened. And then R4 does a pop label, which means penultimate hop popping. He removes the topmost layer and sends a VPN labeled packet to who? To R2. And R2 does a no label, removes everything, and forwards an IP packet to customer, which you can see on R2. If I do 2001, if I receive 2001, which is a VPN labeled packet, do a no label, which means remove everything, and whatever's inside, IP packet, send that to the customer. So this is what happens behind the scenes when you actually activate MPLS. Obviously, MPLS is something that it's pretty straightforward to configure, but most of the times you would have issues if your router ID is not reachable, then you would have issues, or if you haven't activated MPLS. So always use the trace route or ping MPLS or do a trace route to identify what's your transport label, what's your VPN label. Again, if I look at the reverse direction, R2, show MPLS forwarding table. R2 to reach XR1's loopback. This is the transport label, 4004. I don't see a label for the customer 2020, which is XR2. I don't see a label for that because I will not see it here. I would see that in the BGP table. So show BGP, VPN, V4, unicast, all labels. I see that XR1 is telling R2 that if you want to send packets to my customer, you will encapsulate with 19,004, which is my VPN label. So if I actually do a trace route, I see 19,004 as my VPN label, and this is my transport label on top of that. Now, one thing to keep in mind is whenever you do MPLS, your PE routers must always establish the BGP neighborship, IPv4 or VPN-v4, on the loopback. Never on the physical interface. Why is that? Now, let's say I form a neighborship between R2 and XR1 on this interface, not on the loopback. I don't have redundant interfaces, so I don't need loopback, right? But what if this happens? What if I do it like this? The problem is your penultimate hop popping will happen one hop earlier. You know what's going to happen is R2 will send what? Implicit null for this interface. So R4 will put pop label in his out column. For R4, this link is also directly connected. So he will also send implicit null, which means R3 would put pop label in his out column. For R3, this link is not directly connected. So he will send a label, let's say 3000. This guy would send a label down, let's say 6000. This guy would send a label here, 5000. Now I have a packet coming in from customer to customer. This guy does a ping. IP comes here. XR1 puts what? He puts IP, a VPN label 2001, and a transport label 5000. Forwards to R5. What does R5 do? He forwards down here. He forwards 2001 with a label 6000. What does R6 do? He forwards here, again, the transport label, IP 2001, which is my VPN label, 3000. When R3 gets that, what does he do? He does a pop label, which means what he forwards down here is a VPN labeled packet 2001. Does R4 have a VPN label? Does he have any VPN label? No. So he will drop the packet. So your penultimate hop popping happened one hop earlier than desired. So because R4 is not running BGP, so he has no VPN label. The VPN label was only exchanged between 2 and XR1. So R4 would drop the packet because your penultimate hop popping happened 1 hop earlier. That's why you should always establish your adjacency between the PE routers on the loopback. There is an alternate way of fixing this if you don't want to establish on the loopback, which is by configuring explicit null, where router 2, instead of sending implicit null, which he does by default for connected routes, he would now advertise a label. But the only problem with doing explicit null is that now there's no PHP process, which means that end-to-end till R2 will receive something like IP, VPN, MPLS labeled packet. So he would have to remove MPLS, remove VPN, and then send IP packet. So I could do an explicit null, but by default, it sends implicit null. That's by default. So be careful with MPLS, ensure Ceph is enabled, ensure router ID is reachable, ensure MPLS is enabled. Make sure you don't really need to have a unique label range, but you should define a unique label range. It just makes it easier to troubleshoot and identify your LDP neighborship issues by doing a ping MPLS. And that should be more than enough. And again, make sure that your BGP neighborship is on the loopback instead of the physical interfaces. I hope this webinar was informative to you, and thank you for coming in. I'll now answer some of the questions that you must have put up in the Q&A. So let me go back and review some of the questions. I see one question, which is what type of routers will normally be a PE router and what type are P routers? So again, there's no specific definition as such, but then again, the PE routers are pretty much going to be like an iOS XR or ASR router, or maybe an XR 12,000 series. You would never have like a 38 or 39 or 2900 series as a PE, because think about the overheads. You are running IGP, you're running MPLS, you're running BGP. And how many routes are there in the BGP table as of today? More than 600,000 routes. So you should be able to handle those many routes. But for the P routers, which is like R3, R4, R6, R5, they don't need to run BGP, right? That's the whole idea of MPLS. That's the whole reason we run MPLS, because I don't want to run BGP on all the routers. So if I run MPLS, the only thing running on R3 is OSPF and MPLS. That's it. So that those routers could actually be a normal, maybe an ISR G2, or it could be like a normal 2900 series routers. It could be those. Could even be a CSR router. So it doesn't really need to be a heavy end, big router. It could be like a 29, 39 ISR or a CSR, but at least the PEs should be the ASR 9K or maybe a 12,000 series routers. Okay, so the next one that I see is, how come multiple BGP using are related to cost? I don't really understand the question. How come multiple BGP using related to cost? Yeah, I don't really understand that question. I'll move ahead. Maybe I'll come back if you can give some clarity on that. Is it normal to use internal IP address in MPLS inside the ISP network or is it normal to use public IP address in a live network? The internal infrastructure would never be public. It could be, because the thing is that the internal network is never advertised to public. You would never find the ISP's internal network being advertised through BGP. That's only internal to the ISP. So whatever is between 2 and XR1, that would probably be a private IP address. It doesn't need to be a public IP address because it's not advertised. Yes, R2 would have a public IP address, public facing IP address, but internally it would probably be a private IP address. But again, that depends on, let's say if I had 2 ISPs connecting together, then yes, the links between the 2 ISPs would be public. Okay, so I see the next question, which is, does the next hop always choose the global routing table? Yes. So your next hop is always going to be the global routing table, whether you have a VRF or you don't have a VRF, because you actually learn the route from, even if it's a VPN v4 route, you actually learn it from a global, a neighbor who's in the global routing table. So R2 is not inside a VRF. The link towards the customer is inside the VRF, but he himself, for XR1, he's in the global table. So your next hop would always be the global routing table. Okay. So I see a next question, which is, router 1 and XR1 are BGP peered through the inside router environment? Yes. So you mentioned that R1 and XR1 are BGP peers. No, R1 is not running BGP. R1 is customer. The BGP is only between 2 and XR1. So R1 is just a customer. He's not running BGP. He could run BGP with the ISP, but R1 would never run BGP with XR1. He would run BGP with maybe R2. He could run BGP, but there would be no MPLS between R1 and R2. MPLS would only be within the ISP. Okay, and I believe the next question is the same one from the previous question. I see a next question, which would be, would it be possible and useful to select a label range with one label per client router rather than clients' routes? I normally do like giving a label range. So you would see that a unique label range would be given per route for the customer. So you can assign specific labels to a specific customer also. But again, from a scalability perspective, normally you would want to optimize your MPLS. So right now I actually see transport labels for all the interfaces. Technically, I don't need transport labels for 3, 4, 6, and 5. I only need transport labels for R2's loopback and XR1's loopback. So normally you would want to optimize it. Obviously, right now we did not optimize our MPLS. It's just base configuration of MPLS. Okay. Again, the next question is, since using TCP, can 2 distant routers establish adjacency without being directly connected as in BGP? No. I mean, you could if you have like maybe a tunnel between them, but without tunnel, no. Because the LDP is only sent within that same interface. It does not cross the border. About PHP, how it works, like I said, PHP was just a method of the PE instructing the next hop router or the second last router to remove the topmost layer of the transport label, so that he has to do one job less just to reduce processing on R2. So that's why he sends a implicit null label to tell the remote peer that you should remove the transport label and send it to me. Then I see, is the label process the same in iOS and XR? Yes. I mean, allocating is the same, but you don't really have to enable Ceph in XR. It's kind of enabled and can't be disabled. The next question is, what's the maximum limit of the labels that can be put over an IP packet? It depends. I mean, if you're talking about from the range perspective, the number of labels that are available for MPLS is pretty huge. But if you talk about how many labels can be added on top of IP packet, there could be many. There could be a VPN label. On top of that, there could be an MPLS transport label, or maybe there could be another VPN label. Let's say if you had multiple service providers, where you had one ISP1, ISP2, ISP3. In that case, you could probably have, depending on your configuration, you could have maybe 2 or 3 VPN labels, maybe 2 or 3 transport labels also. It actually depends on your configuration, but you can have as many VPN labels or transport labels as you want. It all depends on your config. You will have access to the webinar. I believe you should receive it through email that you registered. I see another question that if we have different VRFs in the same box, how do we see or verify which VRF our IP packet would go to? So again, we have the route distinguisher and the import export, which basically identifies that the route belongs to which customer. At the same time, there would be a unique label for that customer. There would be a unique VPN label for that customer. So when the packet comes in from the remote router, it's coming in with the VPN label, which is assigned to a specific customer. That's how he knows. Again, I see, could I get a brief on route distinguishers and route targets that come into picture when talking about MPLS? So if you notice, actually, before I had configured MPLS, I still had VRFs pre-configured. I had import export. See, from the control plane perspective, I didn't need MPLS to learn about the routes of XR1 on R2. I was learning that through BGP. So the only use case for route distinguisher and route target comes in is to identify that, okay, because a PE may have more than one customer, right? I may have R1 as a customer, I may have R2 as a customer, or maybe R5 as a customer. So I may have multiple customers, and I need to separate their routing table. That's what is going to be done with the route distinguisher and route targets. And then all right, so I see that some of the questions are pretty much the same. So I hope you guys enjoyed this webinar. And if you do have maybe a question later on, you can always email me your question and I can definitely answer that. You could send me an email on Rohit@INE.com. You could email me here and I could definitely answer that. I hope you guys enjoyed, and thank you for watching.